Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're looking at inner product spaces. Inner products, or more generally bilinear forms, define a scalar product between vectors, which is once again structure preserving, just like the linear transformations we've discussed previously in the Oxford Linear Algebra series. As a bilinear form is the more general operator, we'll start there. A bilinear form is a map on a vector space V, which will go from V cross V into our field. And here, as usual with these examples, we will just take the real numbers to be our field F, but this could be more general, and we will in fact discuss this for the complex numbers at the end of the video. But for now, we will do a map from V cross V into the real numbers R. And this map must satisfy two properties in order to be defined as a bilinear form. The first property we want in our map is that it must be linear in the first variable. So written out formally, that's going to say that if I take the inner product, which is going to be defined or written using this angled bracket. So if I take a linear combination in the first position, so let's suppose it's some scalar alpha1 v1 plus another scalar alpha2 v2, and we take the inner product of that with v3. So just to note here, v3 is a vector in the space V. v1 and v2 are also vectors in the vector space V, and since we know vector spaces are closed under addition and scalar multiplication, when we take this linear combination of v1 and v2, we know that also belongs to V. This is all implicit at this point, as these are things we've hopefully established by now. So we need this to be equal to, for linearity, alpha 1 times the first component v1, comma v3, plus alpha 2 times the second component v2, again inner product with v3. So this is going to be linearity in the first position. And then the second property that we must have for the bilinear form is going to be as follows. Very similar, but now we want linearity in the second position. So here we might have something like v1, comma, alpha 2 v2 plus alpha 3 v3. Inner product is the same as if we were to pull out the alpha 2 and take the inner product there with v1 and v2, and then if we were to add that to alpha 3 times the inner product there of v1 and v3. So they look very similar, but it is important that we realize the first one is linearity in this first position and the second one is linearity in the second position. Perhaps the most common example of a bilinear form is actually the dot product, which I imagine most of you are already familiar with. So let's call this example 1, the dot product, and we'll take this in Rn, our standard n-dimensional real vector space. So here, if we have two vectors, let's suppose we had u and v, and we were to take that inner product, then we would simply define this exactly as we would define the dot product. So we could say, well, this is just the same as u1, u2, dot, 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 up to the nth entry, dotted with v1, v2, dot, 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 up to the nth entry. And of course, the dot product means we multiply together, component-wise, and then add them. So this would be u1, v1, plus u2, v2, plus dot, 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 plus un, vn. Now, we want to check that this does indeed satisfy our two properties in order to be declared a bilinear form. So let's consider an example. So we'll just look at the first position for now, but the second one will follow in the same way. So if we were to consider, suppose we have now alpha 1 u plus alpha 2 v, and we take that product with w. Then using the definition of the dot product, we just say, well, that's the same as alpha 1 u plus alpha 2 v dotted with w. But then if we were to write out all of those component by component, the first one is going to be alpha 1 u1 plus alpha 2 v1, all the way up to the same thing, alpha 1 un plus alpha 2 vn, dotted with w, which is w1 up to wn. And now we just multiply out using the rules of the dot product. So they're going to give me this whole of the first thing. So we've got alpha 1 u1 w1 plus alpha 2 v1 w1 plus all of the in-between terms, and then finally alpha 1 un wn plus alpha 2 vn wn. Now, this is the expansion of the left-hand side here of number 1. So now we need to think about, well, what would these look like, these two pieces? But fortunately, we can just group it together to see that. So we can see that alpha 1 is pulled out at the beginning, our scalar, and similarly, we want all of the terms multiplied by alpha 2. So if we group those together, we bring out alpha 1, and then we're left with u1 w1 plus dot 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 up to un wn. And similarly, we get the alpha 2 comes out, and then we've got v1 w1 plus dot 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 plus vn wn. But what do we have in those brackets? It's exactly the dot product, those individual pieces. So this is alpha 1 u with w plus alpha 2 v with w, where again the inner product is defined via the dot product. So we can see that number 1 is satisfied, so I can say so 1 is satisfied, and you can also check, and you should do this as an exercise if you're new to bilinear forms, very good way to get to grips with the definition. So check that 2 is also satisfied. So you'll find that both of them hold, therefore we can conclude the dot product is indeed our first example, our most simple example, I would say, of a bilinear form. Now you may have noticed in the previous example with the dot product that were we to swap the order, were we to swap the roles here of u and v, so to put v in the first position and u in the second position, we would in fact get the exact same product here. So we could in fact say, well, this is actually the same because of the commutativity of the real numbers. u1 v1 is the same as v1 u1. We can multiply in any order. So this is actually the same as if we had v and u. And more generally, if we have a bilinear form which has this property, so we can say if a bilinear form satisfies what we would call symmetry, so u v is equal to v and u, if this holds, so if a bilinear form satisfies this, then it is symmetric. And again, we can see that this is true for the dot product by explicit calculation. Now there is another important property which is called positive definite, which we should also think about at this point. So we say a bilinear form is positive definite to mean that when you take the bilinear product of the same thing, so of u with itself, then the answer is always positive or always non-negative. So explicitly writing that out, it means we say a bilinear form is positive definite. That means, or is equivalent to saying that the inner product, or the bilinear form of v with v, is greater than or equal to 0, and this is for all v in our vector space. And just to go back and be complete, I probably should have said up here that this is true for all alpha 1 and alpha 2 in the reals in our field, and for all v1 and v2 and v3 in our vector space v. But hopefully you figured that out by this point. So we say it's positive definite if this is greater than or equal to 0 for all vectors v, and in fact equal to 0 if and only if the vector itself v is the 0 vector for that vector space. So if we now look at this positive definite property in the context of the dot product, then we will see over here that we take the dot product of two vectors, which are the same, so that's the dot product of v1 up to vn dotted with v1 up to vn, then that is simply v1 squared plus v2 squared plus dot 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 plus vn squared, which we can see is very clearly positive. It's the sum of squares. And the only way this can be 0, because all of these positive pieces are being added, it can only be 0 if each individual piece is 0. And if each piece is 0, the original vector was indeed the 0 vector in the vector space Rn. So we can in fact conclude that not only is our dot product a bilinear form, satisfies that, it's also symmetric, and we can say it's positive definite. And this allows us to conclude that the dot product on Rn is in fact a real inner product space. More generally, we call any bilinear form, so any map which satisfies properties 1 and 2 is linear in the first and second positions. Any bilinear form which is also symmetric and positive definite, then that is called an inner product. So to be an inner product, you need a bilinear form satisfying these two properties of linearity. 2, it has to be symmetric, which in fact, as we'll see, removes the need to check both of these, as if it's true in one and it's symmetric, you automatically get the second one for free. And 3rd, you need it to be positive definite. So to check whether or not we have an inner product, you have to first show your map is a bilinear form, it's also symmetric, and it's positive definite. Finally, if you have a real vector space equipped with an inner product, just like here, we have our real vector space Rn equipped with our inner product, the dot product. Real vector space equipped with an inner product, then that is what we call the inner product space. And we've just seen with our example that the dot product on the vector space Rn, so n-dimensional vectors, satisfies all three properties. It is indeed a real vector space, and therefore our first example of an inner product space is the dot product on Rn. Our second example is going to come from a completely different vector space. And here, in fact, we're going to be talking about functions, and in particular polynomials, within the polynomial vector space. When working with polynomials, we actually define the inner product using an integral. And this may seem vaguely abstract or possibly a little bit random at this point, but if you have studied any physics or any quantum theory in particular, you may actually begin to recognize why we study inner products in this way and why we define inner products of polynomial functions using an integral. To start, we're going to look at a very simple inner product, which is defined as follows. We are going to say that the inner product between two polynomial functions f and g is going to be given by the integral from 0 to 1 of f of x multiplied by g of x and of course we're doing the integral there with respect to x. And this is going to be where f and g belong to our polynomial of degree n space of x, which we've seen before is indeed a vector space. Of course, we need to check that this is indeed an inner product, which means checking that it satisfies our three properties. So I'm going to start with symmetric because, as I've hinted at several times now, once we have symmetric, we only need it to be linear in one position, because then by symmetry, the second linearity actually will follow. So if we consider trying to show that it's symmetric, so number 2, and if we consider, so fg is defined like so, and now I consider gf inner product, which is the integral from 0 to 1 of g of x times f of x dx. Then by the properties of integrals, we can see that these are very clearly the same. We can multiply our functions in any order and we should get the same answer. Well, we will get the same answer. So these are equal, so we can say symmetry is going to hold. Now linearity, bilinear form, again, now we can just consider it in, let's say, the first position and look at alpha f1 plus, let's call it alpha 1 f1 plus alpha 2 f2 comma g. So again, by the definition, that's 0 to 1 of alpha 1 f1 plus alpha 2 f2 multiplied by g dx. But of course, that's going to split up into two pieces, so we can say that is, pull out the alpha 1, we've got 0 to 1 of f1 g dx, and then we've got plus alpha 2 integral 0 to 1 of f2 g dx. And now hopefully you can see these two individual integrals are going to be our two pieces. So this is f1 and g, and this one here is f2 and g in our inner product definition as the integral. So one is satisfied, we've got a bilinear form, it's also symmetric, so that just leaves us with positive definite. So for number 3, we want to consider f with itself. So the inner product of f with f, by our definition, is 0 to 1 of f squared dx. Now we have a square function, a square polynomial function. So this, the integrand, is always positive because, again, it's a function which has been squared. So we have the integral of something that's always positive, and of course the integral represents the area under a positive curve. So therefore this will always be greater than or equal to 0 as well. So again, properties of integrand say this is always positive because we're integrating something that's always positive. And in fact, the only way it can be 0 is if the function is everywhere 0. Because if we have a non-zero bump anywhere, then we're going to have a non-zero area under that bump. So it will indeed satisfy positive definite, and therefore we can conclude all three properties hold, and thus the integral inner product as defined here is indeed an inner product. We can now say that, and because we're taking real coefficient polynomials, we can in fact say that this is an inner product space. For more examples, including others involving the polynomial space, be sure to check out ProPrep, an online resource which provides video tutorials for anyone looking to improve their skills in STEM-based subjects. As with all topics in the Oxford Linear Algebra series, ProPrep offers a number of video lectures to help to solidify what you've seen in this video, as well as numerous exercises, each with their own video solution. Beginning with the standard vector spaces of R2 and R3, there are further examples in Rn, more from the polynomial space, and even an inner product defined over the vector space of matrices. Click the link in the video description below to sign up for your 30-day free trial courtesy of Tom Rocks Maths and see just how much ProPrep can help to improve your learning. When working in an inner product space, there's a very nice way to construct a basis using what is called an orthonormal set. Here's the definition. So an orthonormal set is a set of vectors, let's call them v1 to vn, belonging to in an inner product space, V, such that when you take the inner product between any of them, so if you take the inner product of vi with vj, where I and j can range from 1 through to n, then the answer here is what we call delta ij, the delta function, which is defined to be 1 if I is equal to j and 0 if I is not equal to j. So what this is saying is that if you take the inner product between any two vectors in your orthonormal set, then you will get 0 unless they happen to be exactly the same vector, in which case you will just get 1. Armed with this definition, we can now actually prove the following lemma, which relates back to what I was saying about this being helpful for constructing a basis. So the lemma says the following. For v1 to vn, an orthonormal set, which again means they fit this definition, orthonormal set, then in fact we can conclude that v1 to vn are linearly independent set. So v1 up to vn are linearly independent. So of course, in order for a set to be a basis, it has to be both spanning and linearly independent. So if we have an orthonormal set within our inner product space, this lemma is telling us that we actually have a linearly independent set. So let's prove it. Now, whenever we consider linear independence, or we have to show a set is linearly independent, there is a particularly helpful way of trying to show that property, which is to consider a linear combination of those elements and argue that all of the coefficients must be 0 if the total combination is going to be 0. So we start following that. So we say consider alpha 1 v1 plus ... plus alpha n vn, and we suppose we can create such a combination to be equal to 0, where some of these alphas could indeed be 0, but our goal is to show that in fact the only way this can hold is if all of the alphas are 0. And if we can show that, if we can show that alpha I is 0 for all I, then we can conclude that we have linear independence. So we clearly need to use orthonormality, and we're obviously going to have to take some inner products. So what we do is we start by saying, well, 0 is actually equal to the inner product of vi with 0. Because if we take the inner product of anything with 0, we're going to get 0. That's kind of how inner products work, and that would follow from these properties up here. But now we can replace the 0 inside our inner product with this combination here, which of course is 0. So we can say, well, actually, this is the same as vi, comma, alpha 1 v1 plus ... plus alpha n vn. Now we can explicitly use linearity. So property 1, it's a bilinear form because it's an inner product. So we split this up now, we pull out alpha 1, and then we've got vi comma v1 plus ... plus alpha n vi comma vn. Now is where we use orthonormality. So up here we see that we have a pair of our vectors, and it tells us we can only get 0 or 1. That is the property of being an orthonormal set. Now down here we have various pairs. Now I is arbitrary. We could let I be 1 through to n, and that's kind of what we're going to do. But whatever value we have here, we know from this property of orthonormality that these are all going to be 0 unless I is the same as this number. So I and j have to be equal, otherwise we get 0. So we're just literally going to get vi. So all of these are 0 except when this one, as we count up 1, 2, 3, etc., we will hit I at some point. So what we're going to be left with is alpha I, vi, comma, vi. But now we have vi, so they're the same thing, which is 1. So that's actually just alpha I. So we've got alpha I is equal to 0, what we started with. And again, and you might want to do this to convince yourself, sort of step by step, this is going to work. I could have taken I to be anything. So I could have been 1, and then I would get alpha 1, v1, v1, which is just alpha 1. And then I would have got alpha 1 is 0. And then I'd use I equals 2, I equals 3. And you can count through each step. There are n steps, and you'll show that all of them are 0. Or you can keep it nice and general as I have here and realize that I represents an arbitrary vector and therefore an arbitrary coefficient, and we're going to see that all of them are 0. So therefore the alpha I is 0 for all I from 1 to n, and so that allows us to conclude that we do indeed have linear independence. So now we have linear independence of our orthonormal set. So anytime we have an orthonormal set, this lemma has allowed us to show it will always be linearly independent. So the only thing that's missing from it being a basis is for it to be spanning. However, we've seen before in the video on linear independence, spanning, and basis previously in this series, we've seen that if we have a linearly independent set which has the same dimension as the entire vector space, then it is indeed a basis. So any linearly independent set with the same dimension as the whole space will in fact be spanning and therefore will in fact be a basis. So what this means here is that if we have an orthonormal set which has the number of elements equal to the dimension of our inner product space V, then this is actually allows us to conclude that this is indeed going to be a basis of our inner product space. Now there is a sort of converse result to this lemma, which says that any n-dimensional real inner product space has an orthonormal basis. And not only does it exist, but we can actually construct it explicitly via a process called the Gram-Schmidt procedure. And that is exactly what I will be covering in the next video in the Oxford Linear Algebra series. The final concept that I want to discuss today is that of a complex inner product space. So everything we've talked about so far has been related to real inner product spaces where we are looking at our vector space over the real numbers. But now we're going to change that and actually take our field to be the complex numbers. And in this instance, what we actually want to look at now is something called a sesquilinear form, which is defined as follows. Just as with the bilinear form, we require the first property to be linearity in the first position. So linearity in the first position. But now our second property is no longer linearity in the second position, because instead we have something called conjugate symmetry. So this means that if I have two inner products, U and V, and I change their order, then that is the same as V bar, U bar. So rather than complete symmetry, where they are equal when you swap them, now if we change the order, we have to remember to take the conjugate of each of those elements when they swap position. For the complex inner product space, we again require positive definite. So these two give you your sesquilinear form, and then if we also want the complex inner product space, then that requires a sesquilinear form, so 1 and 2, but you also need the third property, which is again positive definite. So the only real difference between the complex inner product space and the real inner product space is actually this conjugate symmetry. So now we can no longer freely swap the order of the elements within our inner product. We have to take the conjugate if doing that when we're working over the complex numbers. As before, the simplest example follows from something very similar to the dot product, just slightly modified for the complex number setting. So, example. If we have two vectors, let's call them x and y, then we define the sesquilinear form, or the complex inner product, to be equal to x dotted with y bar. So we take the dot product exactly in the same way, but we have to conjugate that second entry. So if we expand this out, this would be x1 times y1 bar plus x2 times y2 bar plus dot 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 plus xn times yn bar. So very similar to the dot product, we just again put a conjugate on that second entry. Because now linearity will follow exactly as before. And again, I recommend checking this. I'm not going to go through all of the details because it's almost identical to what we did for the real dot product. But I will look at number 2 because this one is the interesting one, the new one, conjugate symmetry. So if I now compute, well, what happens if I swap the order? So now I have y bar and x bar. So according to my definition of the complex inner product, I take the first entry, which is just y bar, and I dot it with the conjugate of the second entry. So when you conjugate x bar, you get back to x, you get back to where you started. So that is now going to be y1 bar times x plus dot 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 x1 plus yn bar times xn. And we can see that we do indeed have the bars in the correct place. These two are in fact equal, and so we can see that swapping the order and conjugating them, we get the exact same thing out, which is what we needed up here for conjugate symmetry. The third property of being positive definite again works very similar to what we saw with the real one, but you have this nice additional property which pops out here, which is that if I now take the inner product of x along with itself, then that's the same as dotting x with x bar, its conjugate. And of course, now we're working with complex numbers, we know that this is the same as taking the mod squared, or taking the modulus of our complex number. So this is clearly positive. Modulus is like a length in the complex plane. So this is greater than or equal to 0. And indeed, the only way we can have 0 length of our complex number or our complex vector is if it is in fact 0 or the origin in the first place. That now brings us to the end of today's video on inner product spaces. But before you go, don't forget to head over to ProPrep for a plentiful supply of further exercises with accompanying solution videos, which you can use to really check that you've understood everything that we've discussed. And with a 30-day free trial courtesy of Tom Rocks Maths, you really have nothing to lose. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all very soon. Take care.